talk about the symplectic topology of K3 surfaces via mirror section.
Okay, so as this is the last talk, I think to start with we should thank the organizers and especially Richard Thomas for all the work they've collectively put in to make this conference possible. Also like to record our thanks to the staff here at the Isaac Newton Institute. It was an amazing privilege being Simon's student, and it's been just as much a privilege having him as a mentor and friend ever since, so I'm extremely pleased to speak here. So the theorem I'd like to talk about, which is joint work with Nick Sheridan, another of Simon's spectacular descendants, another of Simon's descendants and a spectacular descendant of Simon's. I blame Mihalis, who's put me off. There's a simply connected symplectic four-manifold X omega for which the symplectic Torelli group, so the kernel of the natural map from the symplectic mapping class group, the group of connected components of the symplectomorphism group with the C-infinity topology, to the automorphisms of the cohomology of X is infinitely generated. And in fact, we'll prove slightly more. So in fact, the group which compares symplectomorphisms up to isotopy just to diffeomorphisms up to isotopy, so the kernel of the map from the symplectic mapping class group to the smooth mapping class group of X surjects onto an infinite rank free group.
So in the second bit, you drop the omega, is that right? The X, no omega not left there.
There's still an omega when I'm talking about it as a symplectic manifold,
yeah.
But omega is not relevant. Yeah. So the difference in the statements is here I'm looking at symplectomorphisms acting trivially on cohomology. In the second statement, there's a slightly stronger fact that this sort of infinite generation is kind of completely invisible to smooth topology. So I wasn't here 23 years ago. I was a master's student in Cambridge, working very hard in the hope that I would be able to become Simon's student. But I was here at the spectacular gauge theory conference 21 years ago, at which Simon talked about Lefschetz pencils, and at which Paul Seidel gave us the first examples in which this group is not trivial. So this is very much a sequel to Paul's talk from 2 decades ago. So to start with, let me describe an example of such a manifold, a particular K3.
But an infinite rank free group, is it?
Yes.
That means free group on infinitely many generators.
A free group on countably many generators.
All right.
That's right. So the example will be sort of a familiar manifold to people in certain communities. So we begin with a certain famous family of quartic surfaces. So lambda is a complex coefficient, and for each lambda I get a quartic surface in CP3. This has a sort of group acting fiber-wise, so if I take the kernel of the map from sort of Z mod 4 to the 4 modulo its diagonal subgroup, and I take the kernel of the addition map from this to Z mod 4, so abstractly this group is just a copy of Z mod 4 squared. this acts by multiplication on the coordinates by roots of unity. Since I'm thinking projectively, the diagonal acts trivially. The function of taking the kernel of this sum map is to look at a part of the group that acts preserving the sort of holomorphic volume form on the fibers of this family, so preserving the fact, respecting the fact that these are Calabi-Yau surfaces. So I can form a kind of fiber-wise quotient, which still then maps to C with coordinate lambda. So most of the surfaces in this family, or all of the surfaces in this family now acquire some singularities. So the general fiber has 6 A3 singularities. So these are the singularities that locally look like quotients of C2, where you identify ZW with IZ minus IW. I, as my friend Oscar likes to tell me, is a choice of square root of -1. And we can resolve those. Actually, we can resolve them in the family. So
W has nothing to do with W and symplectic.
no, this is now a W rather than an omega, but my handwriting when not in LaTeX is dubious. Apologies. Z and W are coordinates on C2. So we resolve these simultaneously to get a family sort of chi-tiddles, which still maps to C. And actually, multiplication by I on the base coordinate identifies the fibers over T and I times T for T in the C plane. So I can take one more quotient and get a family sort of which now maps to the sort of orbifold sort of C divided by Z mod 4. And there are some special points here. So, so the fiber, so I have the fiber over 1 still has a node. So I've resolved the singularities for the general fiber, which is smooth. And that general fiber has sort of 19 obvious cohomology classes. There are 18 that come from resolving these A3 singularities. When I take the preparent resolution of this singularity, I put in 3 rational curves meeting in a chain, and there were 6 such singularities. So I have sort of 18 resolution curves. And I can also think about just the hyperplane class from CP3, pulled back. And the kind of manifold I want to take is the general fiber of this family equipped with an irrational Kähler form. So the theorem applies to X omega, where X is the smooth fiber of this family, which is a K3 surface usually known as the mirror quartic. And omega, or the Poincare dual of omega, is sort of, in this basis, irrational in the sense that its coefficients lambda I are linearly independent over Q. And we'll see where these sort of rather particular conditions come from. Okay, so from the way I've presented this manifold, we sort of learn a little bit about it. So, so from the construction, X sits in a family over, well, this orbifold minus the point 1, where the fiber was actually still singular even after our simultaneous resolution. So let me, for later reference, call this B. So I get a sort of monodromy representation following Peter Kronheimer. I'll write the fundamental group of an orbifold just as pi 1, so this means the orbifold fundamental group. I can think about the monodromy of this family and then how those monodromy automorphisms act on the cohomology of my K3, and I can sort of pull back to the cover corresponding to sort of the trivial monodromy action. So this is a cover with covering group. It's actually one of the classical modular groups, gamma 0 2 plus, but concretely that's just the free product of Z mod 2 and Z mod 4. And then this maps to the sort of symplectic Torelli group, so by definition the ones that act trivially on cohomology. And explicitly, this sort of covering is just a copy of the upper half plane minus some sort of locally finite infinite set of points, the pre-inverse images of this point 1, where I had a singular fiber. So this is an infinite rank free group, F infinity. And if I think about one of the generators of this F infinity, one of the natural generators corresponding to a loop that just went around the point 1, then such a generator maps to a squared Dane twist in the vanishing cycle of that nodal degeneration. And these were exactly the elements that a little over 20 years ago Paul taught us lay in the kernel of this map from symplectic diffeomorphisms to all diffeomorphisms. So somehow...
Is this a Kähler class? Omega?
Yes, it actually lies in the toric Kähler cone for a certain realization of this as a hypersurface in a toric variety.
And this where that infinite rank free group came from?
Yeah, so I've taken an infinite cover of this orbifold, and this orbifold has a puncture downstairs corresponding to the point 1, where I had a nodal fiber in my original family. So actually what this B twiddles is the upper half plane minus an infinite set of points. And the fundamental group of such an infinitely punctured surface is an infinite rank free group.
These infinitely many L's are images of each other under what?
They're images of each other under symplectomorphisms.
What kind?
Well, I mean, under monodromies of this family, but just, what can I say? I mean, under things built out of Dane twists and the order 4 monodromy, but corresponding to complicated paths. I don't think there's anything better to say.
Actually, that's
Oh, sorry, this...
a TS result
Yes, sorry.
from its resolution.
Absolutely, the threefold... Yes.
I was going to say there was a better answer to the question before. I mean, all this dual story is taking place in some Siegel space, a number theory, and the lambdas are very interesting when they're the linear independence. They are correspond to some very big field extension of Q, which you can see from the quadratic form involved, And so you're actually doing some big generalization of the usual story of a half plane, but in a much larger group rank. So they reproduce the usual story of modular forms, number theory, and Siegel spelt that out. Carl Ludwig Siegel spelt all that out. So I mean, maybe where you're ending up is well-known territory. I mean, of course, you've got this big interpretation, you've got your whole process, but when you said it wasn't a good description of what the answer was, I say there is a good description. Look it up in the literature. It's called that. How you get there and how you relate it, you can look at it in detail, but there is a good answer to this question. And the question is very good classical number theory.
Okay, well, I wasn't equipped to give the good answer now. But, okay, so I should of course point out, so this is something we get from the construction of this four manifold. I mean, the free group on two generators contains a free group on countably many generators, so somehow building maps from an infinite rank free group to something isn't going to win you any prizes. So the theorem we're going to prove is that rho splits. And, to do that, what we're going to want is to have the symplectic mapping class group act on something. And the thing that we're going to have it act on is the Fukaya category. So maybe in sort of a tiny bit more detail, what we're going to find is that we have this sort of monodromy representation rho. This came, of course, from just the monodromy of our family to the group of all symplectomorphisms, which acts, it acts on the Fukaya category, and it acts by so-called Calabi-Yau autoequivalences, ones that preserve the natural Calabi-Yau structure of the category. So that has a subgroup of things that act trivially on Hochschild cohomology. That plays the analog of the Torelli group. And what we're going to find is that this map is an isomorphism. So this is really sort of the theorem which implies this and sort of where we're headed. And we're headed there in three stages. So there'll be three ingredients. The first will be to identify the Fukaya category with the derived category of coherent sheaves of a mirror object. So we'll prove homological mirror symmetry, saying that there's a sort of equivalence from this to the derived category of coherent sheaves on some algebraic surface, and the particular algebraic surface will depend on the symplectic form that we've put, the Kähler form that we've put on X. So here, X check will be an algebraic surface. And this is mostly due to Sheridan following a template laid down very much by Seidel. The second stage will be to compute the autoequivalence group on the right-hand side, and that will be by appeal to some beautiful work of Tom Bridgeland and Arent Beyer and Tom Bridgeland. So that's somehow entirely from their results. And then somehow the last stage will be to look at what one has so far and to think just enough about this equivalence psi between the symplectic and algebraic geometry to conclude. So. And as I hope this sketch sort of lays out, somehow, in the very mountainous landscape of mirror symmetry, I think these results of Sheridan and of Byron-Bridgeland are two of the sort of absolute pinnacles, and we're really just sort of stringing a fairly minor bridge between those in order to extract this particular consequence. Okay, so let me say, a little bit, but really very little about the first of these three stages. So if I have a symplectic four-manifold whose first Chern class vanishes, then it has a Fukaya category. So this is a category which is linear over the Novikov field. This is a field of formal series. So the AI's belong to some background field which I'll take to be C. The lambda i's are real and tend to infinity. And Q here is a formal variable, so this is some sort of real power series version of a field of Laurent series or something like that. All that will matter for our purposes is that it's an algebraically closed field of characteristic 0. And
these are infinite sums.
These are infinite sums, so there is content to this last statement. And the point is that Q you should think of as a parameter, a formal parameter recording areas of holomorphic disks, and Gromov compactness is a statement which gives finiteness statements below a prescribed energy level. And so counts of holomorphic disks will naturally be well defined here without having to make convergence assumptions. Although, as Paul explained in his talk, maybe convergence assumptions are finally becoming within reach. So we'll say that x omega is homologically mirror to an algebraic surface sort of x, I'll put a circle for sort of a mirror x circle, and this will be an algebraic surface over this field lambda if the Fukaya category of x is equivalent to some DG enhancement of the derived category of sheaves on x check pulled back by some field automorphism psi. So for us, the particular K3 surface I discussed, X is a resolution of a hypersurface in the toric variety P3 modulo this finite group gamma. And you know, this toric variety is the toric variety associated to a reflexive simplex whose polar dual is actually up to scale the standard simplex. So there's a standard construction of pairs of mirror Calabi-Yau hypersurfaces in toric varieties going back, in this special case, to Green and Plesser and more generally to Batarev. And sort of that suggests that the mirror to hypersurfaces in the toric resolution of this slightly singular toric variety should be hypersurfaces in the toric variety associated to this standard simplex. That's just the projective space, so one expects in our setting sort of X circle to be a quartic. So let me state a sort of boiled down version of the relevant mirror symmetry theorem. So maybe what I should say is that there's a family of quartic surfaces over lambda parameterized by the affine space AI, where I indexes the toric boundary divisors of the sort of toric resolution of this slightly singular toric variety. So our K3 surface X that we care about will sit inside this resolution as a hypersurface. So these toric boundary divisors will be things that we can restrict to get divisors or dually Kähler forms on X, such that given lambda n positive real numbers indexed by these toric boundary divisors defining a toric Kähler form omega lambda on our K3 surface X, there exists some d of lambda in this affine space. So this is an affine space over our Novikov field lambda, such that the valuation of d of lambda is just lambda. That's to say the sort of leading order Q powers in the monomials defining our quartic hypersurface encode the cohomology class of the Kähler form such that x omega lambda is homologically mirror to the quartic sort of x check d of lambda. Okay. So I very slightly lied here. Really, we can't quite take all possible coefficients lambda because there's an issue as to whether or not the mirror you would write down is smooth. But that will never be an issue in the situation in which the lambdas are linearly independent over Q. So sort of in the case where this quartic wasn't smooth, just ignore those lambdas.
Generic fiber is an arithmetical sentence.
Yeah, though I don't quite want to take the arithmetic general fiber, but it's true on a dense open set. So, okay, so I don't want to say much about this. I just want to make a couple of comments and then move on to the other parts of this sort of sketch outline, which I think not more interesting than maybe I can communicate more of significance in a finite time. So the sort of the key ingredient making this possible, or making this accessible to us, which is something about green-Plesser mirror pairs, that's to say pairs of mirror Calabi-Yau hypersurfaces associated to polar dual reflexive simplices, is that sort of the hypersurface sitting inside P3 mod gamma, so this is the one after I've blown down these resolution curves, is naturally a branched cover of P2 such that the toric boundary maps to a union of 4 hyperplanes. So an open subset of my symplectic manifold is an unbranched cover of the 2-dimensional pair of pants. And the symplectic topology of this open pair of pants, which is something that Denis Auroux talked about in his talk in the context of non-compact Lagrangian submanifolds, is very well understood from the point of view of compact Lagrangian submanifolds from Sheridan's thesis, following ideas of Paul in the one-dimensional case. So this contains a famous immersed Lagrangian sphere that Sheridan understands completely. So this gives you a description of the Fukaya category of an open part in terms of something you understand well, and then following a strategy, again going back to Paul, one aims to understand the Fukaya category of the compactification as a deformation. So in the settings in which people have worked before, the compactification devices that you encounter are all ample and sort of individually ample, and you count holomorphic disks weighted by an intersection number with those, and that looks like a pretty good deformation problem because those intersection numbers are positive. Here, the fact that we had to resolve this x bar to get our x means that some of the coefficients of our compactification divisor aren't ample, so you can't set up the deformation theory naively over a polynomial ring or a power series ring. What you have to do is think a little bit harder and work over some ring related to the ample cone of x of those ample classes supported on D. And that's something that Sheridan has developed very systematically and in the context of which he's proved finite determinacy theorems. So this uses deformation theory over a ring related to what I'll just abbreviate for now as amp xd, the sort of ample cone of x, where you look at ample divisors, ample effective divisors supported on D. And this is work that's been developed by Sheridan. Okay, but the essential point is that we put ourselves in a situation where we can reduce to the known Floer theory of Lagrangians in pairs of patterns. Okay, so our next ingredient is to somehow compute the autoequivalence group of this derived category of sheaves.
Is there a version of your theorem in any dimension?
Yeah, but you have to assume that the Fukaya category satisfies a collection of axioms which are all established for, say, versions of the relative Fukaya category, or would all hold if one appealed to Kuranishi structures, except that I'm not quite sure if all of the results that we would use on open-closed maps and the Calabi-Yau property of the Fukaya category have been written down in that language. But sort of, we wrote the paper saying, given a category satisfying these, this mirror symmetry statement holds. In higher dimensions, you should use the Stacky derived category when the mirror is singular. Okay, so Bridgeland, in his sort of beautiful theory, says that an algebraic variety has an associated complex manifold of stability conditions on its derived category. So just in the context of a K3 surface, if the sort of extended Néron-Severi group n of x is given by H0 plus H4 plus the Picard group, well, then a stability condition is a pair comprising a map Z from from this Néron-Severi group to C. This is sometimes called the central charge by Bridgeland, and a collection of subcategories of so-called phi semi-stable objects. And these should satisfy various axioms, and the most important axiom is a kind of filtration axiom saying that all objects of the category can be built out of the semi-stables. So any object E has a Harder-Narasimhan filtration which looks like this. So it's a sequence of arrows starting at naught and going to E, such that the cones, if you complete these morphisms to distinguish triangles in the category, then the things you get should be these sort of special semi-stable objects, and they should have descending phase. So AI belongs to P of phi I, and phi 1 is bigger than up to phi k. Okay. And the sort of amazing theorem that Bridgeland proves is that somehow these subcategories locally deform with this rather benign Z, so the forgetful map from this space of pairs just to the space of Zs is a covering map. So this is something purely associated to the categorical structure. So certainly this carries an action of the group of autoequivalences of the category. And the theorem that Bayer and Bridgeland prove is the following. So let X be the complex K3 surface of Picard rank 1, then there's a short exact sequence which looks as follows. So there's the fundamental group of a certain period type domain, which I'll define in a moment, that maps to the autoequivalences of the derived category as the Torelli type subgroup. So so the kernel is sort of the automorphisms of the cohomology preserving the relevant sort of Hodge structure on the cohomology. So the precise flavor of automorphisms that show up involves a certain orientation condition, and I'll just suppress the details by putting in this benign plus.
B0, this first thing, what was that?
I'm just about to tell you. So if I let P of x0 be the space of omegas in the complexified Néron-Savary group such that the real and imaginary parts span a positive definite two-plane, then this has sort of two connected components, and what I actually want to do is I want to take one of the connected components but remove a countable collection of hyperplanes. So this is one component. You choose a component that, suitably interpreted, contains a Kähler form, and you remove a union of hyperplanes where delta belongs to the set of elements of nx of square minus 2. So these are the sort of Mukai vectors of spherical objects. So here this is with respect to the Mukai form. Think that. So delta is sort of something like the Chern character, the Mukai vector of a spherical object. An object of the category whose endomorphisms are the cohomology of a two-sphere. So we can boil down what this sequence looks like completely in the sort of specific case that is relevant to us. So if I take a Picard rank 1 quartic, then this sort of open subset, this period type domain, well, it also carries a GL2 action. GL2R acts just by sort of acting on C. So this turns out to be GL2R plus bundle over the upper half plane minus this set indexing these classes delta, which is some locally finite infinite set of points, and the sequence becomes 1 goes to an infinite rank free group, that's the fundamental group of this period domain, goes to Z star Z mod 4, and then this group of homology automorphisms in this case turns out to be exactly our friend gamma naught 2 plus from the original construction. So this is, and appears as, the orbifold fundamental group of this base B for this family of quartics that I started with. So let me make a few remarks about this theorem, which sort of may seem, might rightly seem slightly magical. So one remark is that you can define this manifold of stability conditions just using the categorical structure, but it's extremely non-obvious that it's not empty. In particular, there's no known way to just directly compute it on the symplectic side. So, the second thing I want to say is that even in the case of these algebraic K3 surfaces, where this is about as well known as it's ever understood, there's currently no analog of this theorem away from the Picard rank 1 case. So we only have this sort of complete level of understanding in the Picard rank 1 case. And just to sort of very briefly say a word about why that is, because I think it's interesting also to a symplectic topologist. So, so the data of Z is encoded by an element omega, which satisfies this sort of real and imaginary parts span a positive definite 2-plane. And since the Picard rank is 3, there's a sort of unique orthogonal, a well-defined orthogonal vector theta to the plane spanned by the real parts and imaginary parts of omega inside the three-dimensional real vector space nxr. And Beyer and Bridgeland study a flow of the shape d omega dt equals psi times theta, where given an object has this filtration as part of its definition of a stability condition. So if sigma is our point of the stability condition, and we take something like the skyscraper sheaf of a point, it has associated sort of maximal and minimal factors in its decomposition. And psi is I times e to the I pi by 2 of the average of the phases of these. So in other words, you take the sort of extreme parts of the filtration on this particular object, and you write down a flow which pushes them inwards and tries to make this object more stable. So the original motivation for the definition of a stability condition was the idea that these subcategories P phi would be related to special Lagrangian submanifolds of phase phi, and people have sort of imagined this kind of decomposition by and large in symplectic geometry as being perhaps the output of some kind of mean curvature flow. But actually what Beyer and Bridgeland do sort of on the B side is kind of fix the analog of the Lagrangian submanifold and flow the holomorphic volume form to make it have constant phase, not flow the Lagrangian. That seems to be the thing that managed to work. That seems to be an interesting lesson to draw from their work. Okay, so now we look in good shape, which is sort of slightly alarming because there's about 6 minutes left, and so far I haven't really done anything except kind of follow around Nick. So there is, even given this wonderful understanding of the autoequivalence group of this mirror K3, there are still some things that need some care. So a small point is that our mirrors are K3 surfaces over lambda and not over C. So there are some ideas around what's usually called the Lefschetz principle. So I won't write much about this, but just to say that your algebraic surface is defined over some finitely generated extension field of Q. Such things embed into C. That lets you pass Byron-Bridgeland's results sort of reasonably intact from C to lambda. But their results rely on having this Picard rank 1 hypothesis. So we do need to know that some of our mirrors are Picard rank 1. So inside the affine space, sort of a to the I over lambda, there are kind of Noether-Lefschetz type loci of surfaces of larger Picard rank. So the general quartic over the Novikov field has Picard rank 1, but there's sort of a complicated locus in which that's not true. So we have this valuation map from the Novikov field to the reals. So we also have a valuation map from this affine space to a real space, and an algebraic variety under the valuation map goes to some polyhedral complex. The valuation map turns kind of multiplication of polynomials into sort of max inequalities. So this takes sort of the Noether-Lefschetz loci to polyhedral complexes which are defined over Q and actually contained in sort of linear hyperplanes defined over Q. But when I stated the mirror symmetry theorem, I said that the valuation image of the monomials defining my mirror exactly encoded the cohomology class of my symplectic form. So if my original symplectic form is irrational in the sense that I explained, then necessarily the mirror that we encounter is Picard rank 1.
This is not specific to Noether-Lefschetz.
No, in any way. It's just that it's an algebraic variety. Absolutely. And for instance, it also applies to the locus of singular elements, which is something we also need. Okay, so let's sort of summarize where we've got to. So we have this map from the fundamental group of this orbifold via symplectic monodromy to the symplectic mapping class group of our K3 surface, and this in turn maps by autoequivalences of the Fukaya category. On the other hand, we have a map constructed by Byron-Bridgeland, well, I guess constructed by Bridgeland, investigated in the joint work with Bayer, to the autoequivalences of the derived category of some algebraic K3 surface over C, which we can identify via Lefschetz's principal ideas with the autoequivalences of the derived category over lambda of our particular mirror K3, and our mirror symmetry statement says these are equivalent. But the proof of mirror symmetry does not imply that this diagram commutes for any inner automorphism rho. Our proof of mirror symmetry is via kind of abstract deformation theory. So our equivalence of categories matches up, say, the spherical objects in the derived category, which are related via spherical twists to the known equivalences of that category, with spherical objects over here. But maybe those spherical objects have nothing to do with this monodromy map. Maybe they're just random other objects that happen to live in the category. So I think there's a sort of interesting philosophical point here, which is that it's easy to build this upper map, but we have, so far as I'm aware, no symplectic techniques to show this composite is onto. It's incredibly painful to build this lower map, and usually people build it by applying mirror symmetry.
Could I just interrupt here? You're talking here about deformation theory.
I was talking about deformation theory really a little bit ago.
I think you mentioned it here. Deformation theory is an infinitesimal motion. It's like having a connection going around. What you need here is the global theory, the monodromy. Then you'll know that you've got back to the right place. So what's wrong with this proof, in detail, basically it is built on the Lie algebra, not the Lie group, or whatever you like to call it. It is not built on the monodromy, it is built on infinitesimal. Deformation theory is, by nature, semi-linear. And the global stuff has to be different. And if you haven't got that, you'll never get it right. So what's missing here is an approach that does the deformation theory by a global version.
I think that's absolutely right. I think there would be better ways of proving mirror symmetry, not going via deformation theory, but using ideas of family Floer theory that might make this evident. They might not, would depend how it was set up. But nonetheless, in the case at hand, one can rescue the situation. So I'm out of time, but let me just say that the last thing we have to do is, by studying carefully the lattices of spherical objects on both sides, in this case, we can prove that this diagram commutes, or at least we can prove enough of that to conclude. So I'd hope to say some things about certain fourfolds, but I won't. Thank you very much for your attention.
In principle, anywhere one could get information about the higher homotopy groups of the symplectomorphisms from mirror information?
That's a great question, and one I've thought about not with much success. There's a general conjecture that spaces of stability condition should be k pi 1s. That's known in all cases that are known, and that seems to fit with some heuristics about at least so I think we don't have any access to the higher homotopy groups of this via mirror symmetry currently, as I understand it. I think there might be reasons to think that if you tried to build a sort of homotopy theoretic version of the equivalences of the Fukaya category that in principle had higher homotopy, it would turn out to be actually a k pi 1. And that would be special to the Calabi-Yau case. But that might just be a function of my sort of ignorance and naivety at this level of evolution in the subject. Dietmar.
And so, if I understand right, your main theorem would imply that if you consider the space of symplectic forms isotopic to omega, it would have an infinitely generated fundamental group, right?
Yeah.
Zero goes into it.
That sounds reasonable. I didn't think about it. Yeah, I think so.
Sorry. First of all, I wanted to congratulate you on two things. One is you certainly win the competition for the best handwriting. That is non-trivial. I admired it as he went on. It remained good right to the end. Secondly, I certainly congratulate you on giving a beautiful presentation of very interesting results, which, you know. But lastly, I wanted to suggest that you've done much more than you think you've done. Hope you'll like that.
Probably Sheridan.
All right, I'm sure this is obviously a collective contribution by all Simon students and a few other people. What you're knocking on the door of here is Langland's theory. Of course, Langland's theory is a vast project, which bits are known and bits are unknown and the conjectures. And what you've got here is very clearly knocking on the door of that. And it's a very interesting step, because I think this is the one trying to find the bridge that connects number theory to geometry and physics is what I've been looking for all my life. Hope some younger people would do it. And I think that this is an indication that this is being done. It's very serious. Because when you start talking about this, this is exactly the kind of Langland approach that would be associated with the field of the Calabi, of the K3. You talked about extensions of the rational, infinite, and all degenerates. For number theories, they would be in the Galois group of Q bar, Q. That's what's unknown. But they certainly would be realized inside this way. So this is what you'd expect. And but of course, there's only tinkering with it. We've still got vast, but basically it is a very significant bridge towards building the kind of ultimate bridge land or whatever you like, between Langland's, and this is the real Langland, not the geometrical Langland. We know about the work of Witten and all the others about the geometric Langland, but they were for good reasons perhaps stayed clear of the real number theory. This really gets into the number theory. So I think here we have a piece of that big jigsaw puzzle that God created for us in the early universe or whatever it was. And I think this, and a few other lectures in this meeting, which I see pointing in the same direction. So I think this conference, Simon's birthday, will go down in history as the first time people began to understand the Langland's conjecture. There we are.
I'm sure it will go down in history.
How about that as a finishing line?
I think this is a very good finishing line. Yes, and thank all the speakers for that wonderful talk.